All right, in this video, we're going to talk about work and the law of conservation of energy. In this part, we're going to keep it qualitative, and then we'll do the quantitative stuff in the next section. So the first thing is just to define work. We've kind of already talked a little bit about it, but just to put down the definition for it, work is done when a force produces a motion in the direction of the force. So the equation for this is work equals Fx. That's usually how it's left. The x there has to be in the direction of motion. To really specify that, sometimes that equation is written as the cosine of theta times x. So those are the normal ways that you see friction. On the bottom here, you see a couple different images flashing, and this is the way that work could be seen, because another way to talk about work is actually the addition of energy into a system. So work can be done by different things. As I flash through here, I can't pause it, that would be nice. Okay, that one, grab it. So I can't do them all that fast. That's just work set equal to all of the other energy equations that we've seen already. We're going to talk about that some more, so I'm not going to spend more time on that right now. And there's just the equation written out in words. Okay, so important things to note with work is that if you don't move anything, no work is done. We talked a little bit about that. You have to actually produce motion to move. So if you push against the wall really hard, the wall doesn't move, you've done no work no matter how hard you push against it. The other thing, and that's what this first image is down here, the other thing that is a little bit tricky is that if you have a force that is not in the direction of motion, then that force does not count for work. So in this example on the right, if you're lifting a box, if you're just holding the box up, so the force you're exerting on the box is up, and you move to the right, then this force does no work because it's not in the direction of the motion. Now, if the force was at an angle, if the force was something like this, then you would find the component of the force that is in the same direction of your motion, so it would be the x component here, and you would use that x component to find the work. So only the force that's in the same direction as the motion counts. Perpendicular does not count. Okay, a couple things about work here. So change in mechanical energy of the system. So in this example, let's say the guy had the barbell on the ground. If the barbell's on the ground, then it has no energy. As soon as the guy picks it up, he's kind of creepy looking. Anyway, if he lifts that up, he's adding energy into the system by increasing the height of the barbell. So now that the barbell is up high in the air, now it has gravitational potential energy, and if he let go, it would fall quickly to the floor and it would gain kinetic energy as it falls. But before he lifted it, when it's just sitting there, it had no energy. So work is adding energy into the system. Okay, law of conservation of energy. This is what we use with all the problem solving in this chapter. Important to note, you've probably had this one before, but energy can't be lost or gained. It only changes from one form to another. So when we talk about gravitational energy, kinetic energy, elastic potential energy, all of those energy forms can be transferred one to another. Now, we also talked about work. That's not energy being transferred within a system, that's energy coming into a system. Now, if you make your system big enough, I should start with what's a system. A system is whatever you're talking about. If you're talking about a box on the ground, then that's your system. If you make the system big enough, if you make the system the entire universe, then you can't add energy to it, right? Because the energy can't be lost or gained in the universe, right? But if you're talking about just a box, if the box is your system, you can add energy to it. So that's what we're talking about here. So this is about defining the system. So you have to decide when you do a problem what your system is. It's usually it's really easy to figure out from a problem what they're asking you about what the system should be. Okay, so if the system has more energy at the end than it had at the beginning, that's how you know that work was done. So if any energy is added to it, you've had work. Another thing that's interesting is if you have friction, you still have to account for it, but when energy that you begin with turns into friction, that friction energy can't be translated back into another energy form. Friction is basically a useless energy. And if you think about it, friction happens when two things rub together. And when two things rub together, it produces heat. So that's where it says on my PowerPoint here, thermal energy. So thermal energy, then you're not going to use that to, roll a ball down a hill or something like that with the other things that we're talking about. So we do have to account for friction, but it's not going to translate into another energy form. Okay, here's the law of conservation of energy if we leave it as the whole mathematical symbol. And if you look at it, it looks really scary. It's a lot of symbols, but all it really says is that all of the energy that you have at the beginning equals all of the energy that you have at the end. Okay, that's what that whole thing is. So when we look at a problem, and we'll do these mathematically in the next part, but for now, just looking at a problem, we're going to figure out which energy that we have to begin with, and you can even just circle in a problem. I have this energy and this energy and this energy, and then which ones do I have at the end? You may have a kinetic energy at the beginning and the end that are different. So you might have two different kinetic energies in the same problem. Same with any of the other ones. You may have two on the right and one on the left, or vice versa. But this just gives you all of the options for energy you can have at the beginning and energy that you can have at the end. Okay, and we'll do examples of this so you'll have a chance to see it. Okay, what we're going to be looking at in this section is really energy bar graphs. This is just a visual way to represent what's happening with the energy, and then we will then apply the mathematical formulas to the energy bar graphs to solve problems. So here's how it works. You'll have, let's see, there's my empty bar graph. You'll have an empty bar graph. It's generally given to you, so you don't have to draw this from scratch. And your job is to look at a problem and see what energy you have at the beginning, what you have at the end, and make a bar graph representation of it. Here's what you need to know. It's qualitative. That you can make these quantitative, but for now they're going to be qualitative. So you don't know how much energy that you have in this case, since we aren't using numbers, but you can represent, a little bar for a little amount of kinetic energy, a large bar for a large amount of gravitational energy, that sort of thing. So that's all you're doing. But here's the only trick, is that let's say if you start with 4 bars high of kinetic energy, at the end you should account for all 4 bars. So you should start and end with the same amount of energy by showing that your bars add up to the same size from beginning to end. Now the little spot in the middle, the energy flow diagram, what that is the place where we represent work. So how you do that, and I'll show you this on an example in a second, is that you'll have a circle. And then with the circle, you're going to draw an arrow in to represent the addition of energy. So that'd be the addition of work. Or you might have an arrow out to represent that work is leaving the system. I'll show you both of those here in a second. Last thing then to notice, so each of the things, that's kinetic energy, gravitational energy, elastic energy. That should make sense. This is where work happens, where we show that we've added or lost or used work to do something. And then at the end, so you have the same 3, but you also have this 4th one over here, EINT. The INT represents internal, and what that's for is friction. So if you see EINT, that's just friction. So if you have a problem where you have to represent friction, that's where it goes. That's why it's not on the initial side, because you don't start with friction. So you'll only ever see that on the end. Okay, so here's a couple examples for you just to show you how these work. So let's say we have a cliff diver. Looks like fun. Seems like a really bad idea. And you're going to show the energy then before he jumps. Let's see. And just before he hits the water. The really important thing on these is you have to look at the problem and see when they start and when they end the problem, because they could give you this problem and say, that the problem ends when he's halfway down from his dive. So that would be a different ending to the problem. So you would have different bar graphs. So this one at the beginning, when he's just jumping off, what kind of energy does he have? He has energy stored as a result of his position, since he has a height above where he's going to go, as we said in the last video, we make the bottom of the problem 0 for height. So that's why you can say he has height even though he's standing on something. So to begin with, he's got gravitational energy. How much does he have? I don't know. We don't have any numbers. So we just fill it up as a whole bar. At the end, again, they define this problem as the end being just before he hits the water. So just before he hits the water, all of that gravitational energy goes into kinetic. So you would have those two being equal to each other. We don't use the energy flow diagram in the middle because we don't have any work. We don't have anything, any energy that enters or leaves the system, and we don't have friction. They didn't tell us anything about friction. So that would be a really straightforward one. Okay, here's another one. So let's say we have a water well, and the problem is about the bucket. So initially at rest, it is pulled to the top of the well by a hand crank. That's lovely. Okay, so let's say it begins then at the bottom. If it begins at the bottom of the well, it doesn't have any kinetic energy. It says it's at rest. It doesn't have any gravitational potential energy because it's at the bottom of the well. There's no spring involved, so there's no elastic. Okay, so we have no energy to begin with. At the end, I think you can tell that, but since it's pulled to the top, it would now have gravitational energy. So the question is, where did that gravitational energy come from? This is where you use work. So I'm going to use my energy flow diagram in the middle, which you can see is just a circle. And with a circle, I'm going to show that I added energy into the system. So initially I had no energy. I used my arrow in to show that I added it. And at the end, I have gravitational. So that's how those work. The same thing could be true. It says if the order were reversed, what would happen? So if you had the bucket at the top and then you let the crank down and then it's sitting at the bottom, okay? So in that case, you would start with the gravitational energy, and then you would, instead of this arrow being pointing in, you would let the arrow point out, showing that all of that energy left the system. Doesn't matter where you point it out, really, or where you point it in. It doesn't have to be, any particular way. You just have to show in and then out. Notice I make my arrow kind of a bar graphy looking arrow so that I can show that it's approximately the same size as my gravitational energy. It should be exactly the same, but you see what I'm saying there. Okay, here's another one. So let's say we have a slingshot. So with this one, it says just before the launch is our beginning and halfway to its maximum height is the end. So in that case, slingshot looks like I'm going to be using elastic energy. It acts as a spring, right? Now we said if it's rubber, it probably wouldn't work very well according to Hooke's law, but you can still say that there's elastic energy stored in there, I think, pretty safely. So we're not going to use the energy flow diagram on this one because he had already stretched the spring or the slingshot. If he hadn't stretched it yet, then you would say that you did work to stretch it. So again, important to define when you start the problem, when you end the problem. This problem ends halfway to its maximum height. Okay, it has a height, so it's going to have gravitational energy. But if it's not to its maximum height, it's not going to be all gravitational energy. So what else would it be? It's no longer on the slingshot, so there's no more elastic. It gives us no indication of friction, so we're not going to use that. But if it's halfway through its maximum height, it's still moving, and therefore it's going to have kinetic. So we're going to have kinetic and gravitational. Don't worry about the relative heights at this point. We'll calculate that later so you'll know if they're equal or not. But for now, you do know that they have some of each. Okay, and I think that is all we have for this one. So we're going to take a look at some of those qualitatively. Next up, quantitatively, and that's the majority of our chapter. The last thing in this chapter is on power, and I think you'll actually find power is one of the easiest things in this chapter. So this is the tough spot. If you get through these bar graphs and then the calculations with it, you're in pretty good shape for the chapter.